Okay, so definition 9.1. I need to pin myself so I can see what you. Okay, all right, that's clear. All right, a map psi from R to R dash, right, is a homomorphism. Okay, if this is for all A, B in R, right? Phi of A plus B is phi A plus phi B, and phi of A times B is phi A times phi B. So there are two things that you need to check. Okay. If you remember, I remember, but I'm not sure if it's in the class or the class before. I asked you to find the definition of so many different mapping, right? Monomorphism means one-to-one. Epimorphism is onto. And isomorphism is these two plus these two plus homomorphism, right? So this is isomorphism. And if R is equal, if this is equal, the isomorphism is equal to the automorphism. Okay, so we have seen this before, yeah? Okay, look at example 9.1. I think this comes from this marker. Oh, before I forget, there is no class this Wednesday. Why? Hannah?
Wesak Day.
that's a public holiday. We call it Wesak Day. Wesak is the holiday for what actually, Hannah?
I think it's, I'm not sure, but it's something like Paddy. I don't know.
Sometimes we have so many holiday, we don't even realize whether this is like for culture or for for the religion, right? But you can Google. So Wednesday we have no class, right? That's Wesak Day, public holiday. Okay, so this example, we have the mapping, call it pi of I, okay? The direct product of all these rings to I. That's why there is an I. So I define, this is called the n component, right? The direct product. R1, R2, Rn is equal to the specific I. So I is from 1 to n. Okay, so this is like projection on the ith component. Okay, you can define like this. Now, it's not given in my notes, but you have to be able to show that this is an isomorphism. Okay. Homomorphism, sorry, homomorphism. Oh, there is an I here, right? Okay. This is not one-to-one, right? This is not one-to-one. For example, suppose you have 5, suppose you have n is 3, right? Suppose you have so you have okay. Let me put I here. Right? And you can see if you put phi 1 of like 0, 1, 1 is equal to phi 1 of 0. Suppose the ring is integer, yeah? Suppose it's positive integer, is a ring. Like 1, 2, right? So phi 1 of 0, 1, 1 is equal to phi 1, 0, 1, 2, which is I is 1, right? Which is equal to 0, right? But 0, 1, 1 is not equal to 0, 1, 2. So it's not 1 to 1. So in this one, I put maybe RK, maybe the set of integer. So it's not 1 to 1, but it's a homomorphism. So how do you show it is a homomorphism? So you have to find P of phi I of R1 plus R1 dash, right? Okay. So phi I is a homomorphism. Okay, just now I use A, right? So let A be R1, R2, Rn. B equal R1 dash, R2 dash, Rn dash. Then A plus B is R1 plus R1 dash, R2 plus R2 dash, Rn plus Rn dash. And A times B, if you do the normal multiplication, R1, R1 prime, R2, R2 prime, Rn, Rn. Okay, so I erase this. whiteboard. So you had to start with, what is it? Y, right? Y-I. All my mark. What is it? A plus B is, oh my God. Oh, okay. Phi I R1 plus R1 dash plus, oops. I just put this Rn plus Rn. Okay, the answer is Ri plus Ri dash. Then you can separate, right? This is phi I of okay, which is equal to phi I A plus phi I B. All right, and you do the same thing for multiplication. Yeah, you do the same for multiplication. You take phi of this, which is phi of this, which is equal to Ri prime, which is phi of A, phi of B, right? That I think that is clear. Okay. Now I want to move on to the properties. I will not go into the proof, but when you, after the class, you have to try and do one by one the proof. It's quite straightforward actually, but you have to go and do the proof. The same thing with Prof. Ahmad's and Dr. Sanhan. If you want to understand the proof, you have to sit down and redo the proof, rewrite, and try to understand. Okay. This is okay? I haven't seen your thumbs up for a while now. Is this okay? Yes? Yes? Ahmad Hussein, I don't see any sound. Okay, I think it's straightforward. I can give you any example, but if you understand the definition of homomorphism, you can just apply. All right, you just follow through. I can give you any different kind of homomorphism. Okay. Now, properties. Of properties of ring homomorphism. Okay, so I call it as theorem 9.1. Okay. Now, phi of 0 in R is 0 in R dash. If phi is a homomorphism, okay? If phi is a homomorphism from the ring R to the ring R prime, then the 0 in here is mapped to a 0 in here. The same thing like group homomorphism, right? Okay. If we have A in R, then it's a ring, so the inverse, additive inverse is also in R, and the image of the additive inverse of A is just the inverse of the image. It's different, yeah? A There is A here. There is also negative A is the negative inverse. There is the image here. Okay. And this of the negative A is actually the negative of this. For every image side of A in R prime is a ring, so there's also additive inverse. And the additive inverse negative side of A is actually equal to these two, right? Exactly. So this one. The next one is if S is a subring of R, then phi of S is a subring of R. You know, a subring of a ring is just a subset, which is also a ring. Yeah. Okay. So this says if S is a subring, phi of S is also a subring. So this is what, if it is a homomorphism. Now the other way around, if we have S prime is a subring in R prime, then going back, the inverse of S prime is a ring in R, going back. Okay. It's a subring. This is a subring of the image. Going back to the inverse is a subring. Okay. Then last one is if this has a unity 1, okay, then psi of 1 is a unity in R prime. Sometimes we are given these properties, we forget that we can use this in a proof later on. So you have to remember of the basic properties, not only rings, but if you're doing for groups, right? You have to know all these basic properties because you never know that you will use this in your proof, okay? So look at the proof, right? Next one, but the Sanhan mentioned about this, but not in detail. So I will have to define, you remember we define normal subgroup in a group, right? And in the group G, you need to define first the normal subgroup before you can take the factor group. So in a ring, you have to have ideal, right? Before you can take the factor ring. So ideal in ring is like a normal subgroup in group. That is how it acts. I'm not saying that the definition is the same, but that is how it acts. Okay. So what is the definition of ideal? I think after this, I need to go shopping for marker. I left all in my office. This one is like from last year. I think the ink already. Do they sell markers in Shopee or what? I haven't been out of my office. It's just office. I mean house. Office house. I've never been to the shop for so long. Okay. So, okay. And additive. because you have two operations, right? So an additive subgroup N of a ring R A satisfying the properties A N is a subset of N, and B is also the subset of N for all A, B in R. Okay, is an ideal. Is an ideal. This one. Any A in R, you multiply by N is still a subset in N. So you can think about like integer, right? Or even integer. See? Even integer. If you multiply any even integer with this, it's still inside, it's still even, for example. Okay. So this is an ideal on the left or on the right, because sometimes rings, they are not commutative. That is why. If they are commutative, these are the same, right? A, N is N, A. Okay. So the first example, NZ is an ideal in the ring Z. What is it? In the ring NZ. Oh, what is that? I left the Z. Okay, let me do this. Okay, so example 9.2. So actually my R is Z and my N is a subring. I call it NZ. Okay. So NZ is an ideal in Z, right? Since, so you have to show, just take any element A, okay, in Z, multiply with the subring, right? So our N here is NZ. So you take A times NZ and you have to show that it is a subset of NZ. Okay, so you do it twice. One is on the left, but then integers, they are commutative. So AN and NB would be similar. Okay, so let A be new markers. Okay, let A be in Z and N is equal to NZ. Then AN is equal to A and Z. And you have to show that this is equal to inside the subring. So this is equal to an z, which you can call it whatever you want to call it, right? Which is again a subset, right? Subset of n. Okay. All right. Or it's better yet if you want to leave that the n is nz. Okay, I think I better do this. If you put this n of az, this is better because az is a subset of z, right? Az is a subset of z. This is a subset of nz. So this is a subset. Okay, and the same thing you will do with the n. It's a subset of n. Similarly, so this is how you show something is an ideal. All right. Okay. Example 9.3. You have f is the ring of all function mapping real number to real number. And C is a subring of all constant function. Is C an ideal? Okay, so okay, so R is ring of function from R to R. Okay, and C, which is our n, right? N is the subring of all constant functions, right? So by the definition of ideal, we want to show that an is in n, right? Where a is in R, right? Now our n is a constant function. So I said that suppose you take a is in R, any function from R to R. Say take any trigonometry function, sine x. The constant function is like 3. So sine x times 3 is 3 sine x. It's not anymore constant. It's not in n. Okay, that is what I put in the solution. Okay, it's not true that the product of a constant function with all other function is constant. Sine x and 2. So let A is sine x, C, oops, C in C, C is 2. Then you want to show AC is 2 sine x, not in n, right? This the same thing as saying a times n is in n. It's the same thing, yeah? An is subset of n, meaning a times n is in n. But in this case, C constant, right? So I use this n is C. A constant function is in the n. Say maybe just 2, right? So 2 and a is sine x in f. So it's not anymore constant. You can use anything else. not necessarily sin x, it can be fx equal x. So 2 times x is 2x. It's not anymore constant. There are many examples that you can put or a counter example, right? This is again, in this case, is commutative. So you don't have to use the B1. A1 is already not. Okay, example 9.4. Again, f is a function mapping R to R. N is a subring in which all f in f of 2 is 0. F of 2 is 0. Meaning if you put in 2, it's equal to 0. The value, right? Like fx equal x minus 2. F of 2 is 0. Okay. So for this one, you have to check whether it's an ideal or not. So you want to check this. Okay. So I want to use something else, not F. I want to use G. This is F. Okay. So you want to take F in F. A is F in F. Okay. And you take G in N. Right? Because this A is in F. So you want to take F, G, F from here, G from here. You want to show whether it's in here or not. To show it is in here or not, you take the value at 2. Okay? Then what you have to show is equal to 0. But f of g of 2 is f of g of 2 and times, yeah? G of 2 is 0. So it's equal to 0. Right? This is multiplication, yeah? Okay. Oh, this is multiplication, sorry. F2 dot G2. Okay? And you can show the other way around. So it's an ideal. Okay. Dr. Salhan also mentioned about the kernel, right? So the kernel of a ring is the same definition as the kernel of whatever we have learned before. Kernel of a vector space, right? We've seen this before. So if you have a homomorphism, whatever is mapped to the 0 in R prime is the kernel, right? Definition 9.3. Okay. Kernel of psi. So let this from R to R prime. Then kernel of psi equal R in R. Psi of R is 0 in is R in R. Psi of R is mapped to 0 in R. So this is the kernel. So I will give you some mapping and you have to figure out what are the kernels. I think that's straightforward, right? So give that as an example. Identity map. The first one is identity map. Okay, the kernel, what is mapped to 0? Must be 0, right? So the kernel here is just the 0 element. Okay. Okay. Second one. Psi R to R, psi of R is 0 for all R. Okay, so the kernel is the whole R, because whatever you put, it is 0, which is exactly the definition of the kernel. Okay, so one is trivial one is improper one, the whole thing. Okay. Right. This is very important. The kernel is an ideal. The kernel is an ideal. So the same thing we do in group, in which the kernel is always normal, remember? So in ring, the kernel is always an ideal. You have to show that it is an ideal by the normal way, right? For the ideal, skip that, that's quite straightforward. Okay, you multiply R by f of A, right? To show it is in the kernel, to show it is in the kernel, you have to take the mapping, right? So if you have a ring, you want to show An is a subset of N, right? Okay, so you just take any ring R, apply psi of AR, then take out the A, because this is 0, is equal to 0. So since psi of the whole thing is 0, it's in the kernel. I think this is quite straightforward. You can rewrite that proof. Okay. For 9.1 exercise, I call it exercise 9.1. This is actually a quite simple property of a ring. Okay, it's quite straightforward. I will give you hints of why I say it straightforward. It's by homomorphism. I think groups also we did this. If f from R to R prime is a ring homomorphism, then we have f of NA is equal n of FA. Okay, and this n A is in R and n is in Z. Normally we talk about the positive, but for the negative one, they are just the additive inverse. Okay. You see, if n is 2, so you will have like this, right? Right? Which is two of this, or adding to this, a ring homomorphism. What is this? 2A, sorry. 2A is A plus A. Okay, what is this? Right, this is 2 f of A. All right. So if it's 3A, A plus A plus A, so by homomorphism, right, you can get FA plus A. The second one is multiplication. F of A to the n, right, is F of A to the n. Okay, the same thing, right? F of A to the n, the proof is like this. This one I'm just showing you for 2, but you can write the whole proof quite easily. F of NA is F of A plus A plus A n times, right? Which is equal to FA plus FA plus FA n times. So it's n times F of A, right? Then same thing for this one you can do. So you take this F of A to the n You have n times here, you have n times here. So it's straightforward for this one. Okay. Next exercise. Prove the composition of two ring homomorphism is a ring homomorphism. Composition. If F is a homomorphism, G is a homomorphism, why F composition of G is a homomorphism. Also, you have to write it down. Next class is next week. I will ask you. Hannah, you judge this. It's quite straightforward. If I write, I will give you the answer. This F, G, homomorphism. F composition of G is a homomorphism. Okay, this is for next class. This is exercise 9.2. If F is a homomorphism and G is a homomorphism, then F composite G is a homomorphism. So you know you had to show two things, right? Given F is a homomorphism, for F of AB is F A plus B is FA plus FB. See, if I will give you the answer. Now you take F composition G, take with A plus B, separate, it's quite straightforward. Okay. Theorem 9.3. Theorem 9.3, psi is a ring homomorphism with a kernel H, right? If A is any element in the ring, then you take psi of A, which is the image, and then you take back the inverse of the image, you get back not only A, but A plus H. Everything that you go and back forth, you get A. Okay, this theorem shows that if you have A, let me draw. If you have A in R, wow, like if you have A in R, okay, from this A, you will get C of A. From this C of A, you go back, you get this whole thing, okay? So from this A, you get psi of A, but you take the inverse, it got you to this whole coset. This is what it means by the theorem. Okay. Corollary 9.1 is similar in the group. A ring homomorphism is 1-to-1 if the kernel is 0. So this has something to do with A minus B in there, right? If A minus B is 0, A is B is 1-to-1. I think you have done this as before. Okay, so that is the homomorphism of a ring. The next part of this chapter is on factor ring, or sometimes we call it a quotient ring. Dr. Sahan mentioned about this in his somewhere in his lecture, but I will explain more. Okay, so we need to have an ideal. We need to have a ring, and we need to have an ideal. Okay, so if you remember groups and quotient groups, G is a group, N is a normal subgroup, G mod N is factor group, then you do the same thing for ring. R is a ring, I is an ideal, R mod I is a factor ring. So it's very, very similar. Only that R has two operations. Okay. All right, so I is an ideal. So we write R mod I, R a ring, I and R mod I is a factoring or quotient ring, right? And the elements of this is in this form. R plus I, we put, I don't want to put I here because I is normally for identity, right? But this for ideal, R plus A. Okay, and A is an element of ideal. And this is for all R. So this coset in a ring. Okay. So if I is an ideal, then R mod I is called a factor ring or a quotient ring. All right. Now, look at the theorem, theorem 9.4. We have psi R to R prime, ring of homomorphism. We have the kernel H. You know kernel, just now I mentioned kernel is always an ideal, right? So for this coset in this H kernel, so if H say is a kernel, it's an ideal. And the same thing like group before. This is how we define the coset. Suddenly this marker works. I don't know. After a few minutes, warm up. Okay, and the same thing as before, right? When we multiply, is equal to A dot B. Okay. Okay. Right. Okay. So this is the factoring, yeah? This is the definition of our factoring. Right. And we have theorem 9.6. I mentioned this during the homomorphism theorem last time, if you remember. Then we have for ring what we call a natural homomorphism. Okay, natural homomorphism. You have okay, you have a mapping G from R to this factor group. R is a ring. Okay, I is the ideal. You have a mapping from G from R to the factor group. And you define from A, you get a coset, A plus I. Okay, and is a homomorphism. Is a homomorphism. And called a natural homomorphism. Okay, and the kernel. Oh, this is a typo here. Kernel of G, not F. Hannah, you help me correct that, right? Kernel of G is equal to the ideal. Okay. Kernel is what is the element in R which is mapped to the 0. And you know the 0 in a factor group, the 0 here is all element in I. You remember the coset last time? Whatever element in the basic subset or subgroup, the element inside here, the coset is also in there, right? So the kernel is whatever element in here, because this element plus this is I, right? Okay. Right. Now, isomorphism theorem for rings is very, very similar to the isomorphism like we did last time. You remember first isomorphism theorem, second isomorphism theorem, third isomorphism theorem. Okay, I just want you to just go through the proof, but you are not responsible to memorize. Understand? It's okay. Go through the first isomorphism theorem. Let me write and explain. I'm not going to go through the whole proof, but it's quite simple that you go line by line. You can understand that. So, theorem 9.7. First, isomorphism, right? So let F from R to R prime be a homomorphism. Then F of R is an ideal. And F mod, R mod. R mod kernel of F is isomorphic to okay. Okay. Okay, your next second assignment is to find one example for each of the theorem. Okay, find one example for each of these theorems. Now I go to the second isomorphism theorem. Second isomorphism theorem. So you did assignment for this one last time, right? And then is it our test? Did I put in our test? Yeah. Last question in the test, right? About the isomorphism theorem. But this one is a little bit different. If I and J are ideals, okay, of a ring R, then the intersection of two ideals is also an ideal. you can show that too easily. Wow, that is a very good test question or final question. Easy. If I and J are ideals, the intersection is also an ideal. So you can do the factoring, right? So I mod I intersection of J is isomorphic to I plus J mod J or mod I. I think both can be mod J or mod I. Okay. When you go through one by one, the proof, if there is a typo, you will definitely see it. Okay, let me know, yeah? If there's some kind of, I think it's okay. I've gone through this few times, might be still typo. Okay, the proof is not that difficult. It's quite straightforward. Okay, then we go to the last one, which is the third isomorphism theorem. Okay. If I and J are ideals of a ring R, we need to have I is a subset of J, then R mod I, mod J mod I. The quotient of the quotient ring is isomorphic to R mod J. We want this. This is the smallest one, I. Okay. So this one you have like a coset in the coset.